Hello everyone, I'm Hiyab Mekonnen. I'm currently a rising third-year PhD student in Material Science and Engineering at Northwestern University. And today I'm going to talk a little bit about catalysis, or breaking down barriers. I'm basically going to be talking about a chemical technology that is used to cut energy costs. So what is a catalyst? I call catalysts the facilitators of reactions. Some people call them the magic hands of reactions. So let's find out why people call them different names. Think of a chemical reaction as pushing a rock through a mountain. It's very energy intensive and it takes a lot of time. But what if we get creative and create a tunnel through that mountain? We're going to cut down the amount of energy we're using to push up the rope, and we're going to be cutting the amount of time. That's what a catalyst is. Think of a catalyst as the tunnel. If we use a catalyst, we're going to be cutting down the amount of energy that is required to complete a reaction, and we're going to be reducing the amount of time that's required to complete a reaction. So basically, what a catalyst is it's a material that creates an alternative pathway by reducing the energy costs and the operation time to complete a reaction. And catalysts, they affect our daily lives. Think about the building we're in, the wearable devices we have on, the clothes we're wearing, the chairs you're sitting. Everything they have to go through a chemical manufacturer. They have to go through a chemical process. And manufacturers, they want to reduce the amount of energy that they invest. They want to ensure that they don't have a lot of operation time, and they use catalysts to ensure that. Basically, a catalyst is a way to make manufacturers have an economic process. And why do we talk about catalysts so much? If we see the amount of our global energy intake, 87% of our global energy comes from non-renewable resources such as oil, coal, gas, and nuclear energy, which are not environmentally friendly. And manufacturers, they want to make sure that we have a more environmentally friendly process by cutting down this. And they want to use a catalyst to ensure that. So a catalyst, not only does it reduce the amount of energy, but it's also important in making sure that we have an environmentally friendly process. So it creates an alternative pathway. In my research, I studied catalysts for polyurethane production. So what are polyurethanes, first of all? Polyurethanes, they're like a fancy name for foams. So they're used to make up our chairs, our sofas, our couches, our mattresses. So they're just foams. But we call them polyurethanes because we like to be fancy in chemistry. And my catalyst that I use to study this is called FAB, or for short practice, or for short FAB. And even though it's very important, because polyurethanes, they are very important because annually we think that we are investing $7 billion to produce them. So they are very important commodities. So why do we study this catalyst? Even though this catalyst is very important in reducing the amount of energy required, it does have some limitations. So what are some of the limitations this catalyst has? A catalyst has a limitation because of the manufacturing conditions. So a catalyst typically goes through a reactor such as the one shown on the right. So in these reactors, we have high temperature and high pressures. And this makes the catalyst decompose. And when a catalyst decomposes, it loses its ability to facilitate reactions. It deactivates. So remember the image I showed you first about a catalyst being a tunnel? These conditions, the high temperature and the high pressure, it's like mud in storm. It will block the tunnel that we have formed. So if a catalyst decomposes, basically we're going back to square one, and then we're going to have to invest a lot more energy to complete that reaction. So it's important to understand how a catalyst decomposes when it is put in a chemical reactor. So how does a catalyst decompose? There are many ways a catalyst can decompose. There are various pathways, and we need to understand how it decomposes. So for example, my catalyst, it can decompose in such a way that it loses the small red ball first, and then it loses another red ball, and then it's just one red ball and one big blue ball, and then finally we'll just have the blue ball. Or chemically, it looks like this. So when this happens, we go back to square one, and we'll have to invest more energy in completing our reaction and forming our polyurethanes or foams. What are the other ways a catalyst can decompose? Here, I'm going to show you what we call a scavenger molecule come in. So the green ball is a scavenger molecule. It comes in and it breaks two bonds instead of one bond, and it removes two small red balls. And at the end of the day, we are going to be remaining with just the one big blue ball. So these are the two different ways a catalyst can decompose. But we don't really know how it decomposes, and that's why we study them. If we understand which route it follows or which pathway it decomposes, then we can understand how to stabilize it. If we stabilize the catalyst, then the catalyst can have a longer lifetime, and we'll have the less energy intensive process during the chemical production. So what are some of the ways we can understand how the catalyst decomposes? We have two tools. One is computational modeling, the other one is experiments. For computational modeling, we use something called microkinetic modeling. It's basically putting numbers to find the most probable way in which the catalyst decomposes. It's basically like a statistics. And we also do experiments in which we simulate real-life reactor conditions to see the way the catalyst decomposes. So if we understand how a catalyst decomposes, then we can understand how we can stabilize it, and then we can maintain our less energy process during chemical production. And with that, I'd like